Welcome to this video on nuclear fission. In this video we're going to take a look at three different things. First, what the mechanism of nuclear fission even is. Second, how to balance a nuclear fission reaction. And finally, how to figure out or calculate the amount of energy that's released in the nuclear fission reaction. Again, I'm using images and sample problems from the openstacks.org physics texts, and I have links in the description below so you can check those out for those awesome resources and extra problems. Now, you probably know about nuclear fission in the form of an atomic bomb, and that is actually one of the applications of nuclear fission, where we can bombard a nucleus, split it, and release large amounts of energy in a runaway reaction. But in a much more controlled environment and in a much more useful and clean form of energy production to generate electricity, we can actually do nuclear fission in that controlled environment and produce an energy that doesn't have very many pollutants like burning coal. Now the issue is, if there's some sort of natural disaster or oversight on the safety mechanisms, what can happen is the process can become uncontrolled and we can have what we know as a nuclear meltdown. We're not going to talk too much about that because we want to get some basic general understanding of what nuclear fission even is. The basic mechanism you can see here in the picture is that we take a radioactive isotope, this is uranium-235, and we bombard it with another neutron. Now, in doing so, we create an unstable form of uranium, or an even more unstable form of uranium, which is uranium, in this case uranium-236. Now, this is a product of this reaction here that is very short-lived, and because it's very unstable. Basically, the neutron, in adding extra mass and causing deformation of the nucleus, is going to cause the nucleus to split apart into what we refer to as fission fragments. These two fission fragments are actually different elements than the uranium that we started with. In doing that, we produce three free neutrons here to continue the reaction and a lot of energy. So when this was first done by Enrico Fermi in the 1930s, he was trying to bombard isotopes with neutrons to try to make more isotopes. And when he checked what his products of the reaction were, he couldn't find uranium anymore. And so several years later, Otto Hahn and a colleague, Fritz Strassmann, were the first to actually figure out that the reason that you weren't finding uranium was because it had split up into other elements. And so we're going to take a look at how that happens here. So let's try to write it out in chemical equation form. So we're going to take a neutron, and the neutron of course has atomic mass of 1, no atomic number in terms of the charge here. We're going to add it to the uranium-235, this isotope, and the uranium-235, remember, its atomic number is always going to be 92 because it's uranium. And I'm going to show the unstable product here. Obviously, just by adding these things together, we get the new isotope mass, and it's the same element, uranium. And this is unstable and short-lived, so it's not going to be there for very long. What then happens is we get this splitting up, and the solution or the products that are formed here can be a variety of different things. The first thing I'm going to do is I'm going to write in that I have 3 neutrons. These are ones that are not attached to the new nuclei. And these can each go on to do what the first neutron did. And so you can see this compounding chain reaction that can occur. What I'm going to show here in addition is that in this example, we're going to form barium, which is element 56, barium isotope of 141, and then we're going to also form krypton, which is element 36, and it has 92 as its atomic mass. So what happens here is that there's also going to be some energy formed in this reaction, and that's the whole point of this being useful in some ways, to harness this energy. And what we're going to do here is calculate this energy by using the idea of the mass defect. Now this mass defect over here is going to be the difference in the mass of the reactants and the mass of the products of the reaction. The missing amount of mass is actually going to be now in the form of energy. So if we remember the idea of mass energy conservation says that mass and energy are basically the same thing, and where one is lost in a particular form, it shows up in the alternate form. So mass and energy are basically interchangeable. Now what's really interesting in these kinds of reactions is that the products here, in this case barium and krypton, are not always the products. So the fission fragments can be other things. Some example combinations are that we could get xenon, which is element 54, and we have, of course, an isotope version of that, and also strontium, which is element 38. And in this case, there's only going to be 2 free neutrons produced. And another reaction, we can form tin, 132, and molybdenum, 101, and then 3 free neutrons. So you can see that there's different combinations here. And the predictability of this is somewhat wild. So basically what we have to do here is do what we did when we were looking at thermodynamics and look at the idea of what we refer to as statistical mechanics, or in here, statistical quantum mechanics. And what we're looking at with statistical mechanics is what are the possibilities, and then what are the probabilities of the outcome. So what is most probable versus what is most possible. And so we know that there's different possibilities here, and so we can get a probable prediction of what is most likely going to be the result, but not necessarily what exactly is going to be the result. And there are other ways to control it, but we're not going to get into those details. Now let's just look at one more thing before we figure out how much energy is released in this reaction. And that is the chain reaction, the runaway reaction. So we look here, we see we again have our uranium 235. We bombard it with a neutron. It splits up. In this case, they're showing krypton and barium. Then the 3 neutrons from that are each going to infiltrate or bombard another uranium 235 neutron. Because think about, if you have a beaker full of uranium 235 or a bucket full of it, that it's made up of a lot of atoms. So each one of those atoms can interact with the free neutrons from the experiment, and then that creates the runaway process. And you can see this could be an uncontrollable chain reaction. Luckily, we do know how to manipulate and control this reaction, so we can use it in a much more specific and controlled environment. Let's take a look at the energy, though, that's actually being produced and see how we can actually calculate that. So what we're going to do here is take the example of uranium 238, and we're going to show it breaking into strontium, which is isotope 95 here, and we're going to do xenon 140. And of course, we're going to have 3 neutrons left over. Now what I'm going to write here are some atomic masses. So these atomic masses, remember, are what are most important in figuring out the difference in mass between the reactant and the products. And so we're going to have that the mass of the uranium 238 is going to be equal to 238. And remember, there's always these decimal values that are very important, so we actually do have to write them out because that will be where the difference is formed. We then have the strontium 95. The mass of that is going to be 94.919388. And again, these are in unified atomic mass units. We then have the mass of the xenon 140, and that's going to be 139.921610 unified atomic mass units. And then of course we have to account for our neutrons, and the mass of the neutron is going to be 1.008665 unified atomic mass units. So as always, the energy release is equal to the mass destroyed, or the mass changed, times the speed of light squared. So we have to find the difference in the mass between the parent uranium-238 and the fission products. So let's go ahead and do that. Let's find the mass of the products first. And so what we're going to do here is take the mass of the strontium, the mass of the xenon, and the mass of 3 times this neutron mass. So I'm going to take all of these and I'm going to add them together. And what I get is 237.866993 unified atomic mass units. Okay, and the mass lost in this process is going to be the mass of uranium-238 minus the mass of the products. And so if I actually write this out, I'm going to have the mass defect, or the difference, or the mass that is effectively destroyed will really just change into energy. So I'm going to do the 238.050784 minus 237, this value over here, 0.866993, and what I end up getting is this value 0.183791 unified atomic mass units. Now I'm going to make the conversion into mega electron volts per c squared and then multiply by c squared, and that, remember, will get me the energy. So I'll do my energy is equal to the mass defect times the speed of light. I'm going to put the mass defect here and convert it at the same time. So I'm going to take my atomic units here, 0.183791, and I'm going to say that this is, remember again, 931.5 mega electron volts. Okay, and then we're going to multiply this by c squared. Oh, and we need to make sure we put our c squared over here as well. So essentially what I'm doing here is I'm taking the atomic mass units and putting it into this mega electron volt unit. When I multiply by the c squared, that of course will be eliminated. And what I find is that I have 171.2 mega electron volts. Now that's the energy released in just one of the reactions over here. And then of course that's going to be multiplied many, many more times through.